Hello again. This is Math 2, 115 coming to you from the College U page. And the title of this lecture is Counting Elements in Disjoint Sets and the Addition Rule. Make sure you're an active learner as you watch this video. Previously, we discussed counting problems that could be solved using possibility trees and the general multiplication rule. Here we're going to look at counting problems that can be solved by counting the number of elements in the union of two sets, the difference of two sets, and the intersection of two sets. And this is one of the basic rules. This is called the addition rule. It can be proved by induction on K, but most of my students tend to think that this is pretty straightforward. So here we go. Suppose a finite set A equals the union of K mutually distinct disjoint subsets A1, A2, all the way up through AN. Then the number of things in the finite set A, the number of elements in the finite set A, is equal to the sum of the elements in the other sets because they are disjoint, the other subsets. Let's apply that to a problem. So let's look at the example, counting the numbers of integers divisible by 5. So the question is, how many three-digit integers from 100 to 999 inclusive, that means both endpoints are in, are divisible by 5? Well, one way to approach the problem is to look at three digits that are divisible by 5, three-digit integers divisible by 5, and either they end in 0 or they end in 5. And that takes care of all the ones that are divisible by 5 from your divisibility rule. Now, if you add these two things together, that in fact, because of the divisibility rules, when I say add, you take the union, that takes care of all of them, and certainly disjoint, because it can't end in 5 and also end in 0. So what we're going to do is we're going to say, suppose they end in 0. Well, if they end in 0, that means there are possible choices for the leftmost and middle digits, because the rightmost digit must be a 0. So that means there are 10 choices, and there are 9 choices, and there are 10 choices because it has to end in 0. That means there's 90. Similar reasoning, if it ends in 5, you put a 5 there, and you get 90 there as well. Those are disjoint sets, so you add them together, so there are 180 possibilities. That's the same answer we got before, but a different kind of reasoning this time. We also have a theorem, and this follows really from the first theorem. If A is a finite set and B is a subset of A, then the number in A minus B, we defined what this was earlier, is the number in set A minus the number in set B. Now if you think about that, A then is composed of two disjoint subsets. There's what is in B, and we'll just call that K elements for now, and what is in A minus B, which has to be n minus k elements if A adds up to being n elements. And these are disjoint sets because A minus B is A intersect the complement of B. So you see, if we just apply the rule that we had in Theorem 1, we will have that the number in set A is the number in set B plus the number in A minus B, and we can solve for this. And so when we use algebra to solve for that, we get the number in A minus B is number in A minus number in B. Okay, let's look at another example, and this is counting, and this is also similar to a problem that we talked about before, but we're solving it differently this time using some of the machinery that we've developed. Counting the pins with repeated symbols. So consider again the pins discussed in a previous example, and I'm just reminding you here, these are made up from exactly 4 symbols, chosen from 26 uppercase letters of the Roman alphabet and the 10 digits. Okay, and we learned last time that there are this many pins with repetition allowed, and there are this many pins with no repeated symbol. So the question I'm asking you now is, how many pins contain at least one repeated symbol? Well, if S is a set of all the pins with repetition allowed, and A is a set of pins with no repeated symbol, then S minus A is a set of pins with at least one repeated symbol. And you want to think about these things as you're doing this problem. And then by the difference rule, the number in S minus A is the number in S minus the number in A, and we just subtract those two numbers and this one number we had from before, and we will get this as the number. And so there are 256,896 pins that contain at least one repeated symbol. B, if all pins are equally likely, what is the probability that a randomly chosen pin contains at least one repeated symbol? Well, we take the number of repeated symbols divided by the total number, and we get 15.8%. Another way to do it is to use this equation. The probability of S minus A is the number in S minus A over N of S, and that is this. Now we divide this N of S in both. When we divide N of S into N of S, we get N of S over N of S, which is 1. And this is N of A over that. But this is going to then be 1 minus the probability of A, and that is 1 minus 0.842. That was from a previous example that we did in the last lecture, and that also gives us 15.8, the same answer. But solution 2 allowed us to illustrate a general property of probabilities, that the probability of the complement of an event is obtained by subtracting the probability of the event from the number 1. The probabilities must add up to 1. So here is something we're going to talk about later, but if S is a finite sample space and A is an event in S, then the probability of the complement of A is 1 minus the probability of A. And we'll talk about that later in a bit. Let's look at another example. Here we're talking about passwords with 3 to 5 letters. A certain computer access password consists of 3 through 5. That means you must have at least 3, but you can have up to 5. Uppercase letters chosen from the 26 letters of the alphabet with repetition allowed. So how many different passwords are possible? Well, you see, when you think about this, either your password is of length 3, length 4, or length 5. Those are disjoint sets. If it's of length 3, it's not of 4 or 5, and so on. So these are disjoint sets. And so by the addition rule, we just can add those up. And so what we're going to do is, how many passwords have length 3? Well, we can repeat things, so it's 26 times 26 times 26, or 26 cubed. With 4 is 26 to the 4th, and 5 is 26 to the 5th. So if you add all those numbers together, and again, you want to use a calculator probably for this, you get this answer. Let's look at problem B. How many different passwords have no repeated letter? Well, if there's no repeated letter, if you have 3, it would be 26 times 25 times 24. If you have 4, it would be 26 times 25 times 24 times 23. If you have 5, it's 26 times 25 times 24 times 23 times 22. It is this number. Okay, and that was part B. How many different passwords have at least one repeated letter? Well, by part A, the number of passwords was this, and by part B, this do not have a repeated letter. So if you take the difference between the two, you will get this as the number of passwords with at least one repeated letter. Last but not least on this example, if all passwords are equally likely, what is the probability that a randomly chosen password has at least one repeated letter? Well, we're going to take the number of places where password has no repeated letter over the total number of passwords, and we will get 33.1%. So the probability that we have at least one repeated letter is this. Actually, it should be at least one. It should be 1 minus that. Yeah, it should be 1 minus that, so it's 67. Let's look at another example, the number of Python identifiers of 8 or fewer characters. In the computer language Python, identifiers must start with one of 53 symbols, either one of the 52 letters of the uppercase and lowercase Roman alphabet, or an underscore. The initial character may stand alone, or it may be followed by any number of additional characters chosen from a set of 63 symbols. The 53 symbols allowed as an initial character plus 10 digits. Certain keywords, however, such as and, if, print, and a number of others, are set aside and may not be used as identifiers. In one implementation of Python, there are 31 such reserved words, and none of which has more than 8 characters. How many Python identifiers are there that are less than or equal to 8 characters in length? A really good exam question. The set of Python identifiers with 8 or fewer characters can be partitioned into 8 subsets because it can be of length 1, length 2, length 3, and all of these are disjoint, but you have to say the reserved words are part of that set of Python identifiers with 8 or fewer characters. So this is disjoint sets. Now, according to the rules, then, for creating Python identifiers, there are 53 potential identifiers of length 1, and then we can have the 53 times 63 of length 2, and we can have 53 times 63 squared of length 3, all the way down to 53 times 63 to the 7th potential identifiers of length 8, and these are all disjoint. Thus, by the addition rule, the number of potential Python identifiers with 8 or fewer characters is, you add those all together, but you have a common factor of 53. So we factor out 53, and what is left is 1 plus 63 plus 63 squared plus 63 cubed plus ... all the way up to 63 to the 7th. Now, we proved a theorem in an earlier chapter because that is a geometric series. Previously, we proved that by induction. Now, what we're doing is applying that theorem, and so that means it's 53 times 63 to the 8th minus 1 over 63 minus 1, and that gives us this number, a very large number. Now, 31 of these potential identifiers are reserved, so by the difference rule, the actual number of Python identifiers with 8 or fewer characters is, and you subtract the 31, and you get this as your final answer. Again, you want to use a calculator on problems like this. We mentioned Python, and Python right now is the most popular coding language, and you can see the order in which these things happen. I don't know if this is by lines of code or number of people who use the programming language. I almost bet it's number of people who use the programming language, because I know for many programming systems with large lines of code, these are used a lot. So this is probably by what percentage of the people program in this language. I just make note, this is a symbol for Python, by the way, and many of you will probably study Python at the College of DuPage. Maybe you already have. I'm contrasting this with the programming languages that I have programmed in. I guess I left BASIC off this this list, but Fortran, these are simulation language that I used. PL1, which was IBM's programming language 1. This was COBOL in business. At Bell Labs, I programmed in C. I also used statistical S, which is a precursor of R. And now I'm programming mostly in these two languages. Actually, I'm not programming a whole lot right now. But you see, things change rapidly, and so you need to try to stay current. Let's talk. Previously, when we proved that formula for the geometric series, we did a proof by induction. And sometimes when you do a proof by induction, you say, I don't really know what happened in that proof, other than I did prove it using the induction technique. Here's a direct proof. If we let S be A times AR plus AR squared plus all the way up to AR in minus 1, which is what we had before, and then we multiply all the way through by R, you see that the power becomes increased by 1. And then if I subtract these two, so I'm taking S minus R times S, so this one minus this one, many things cancel out. The only thing that doesn't cancel out is the first term and the very last one. So it is A minus R. But then I can factor the s out of this side, and I get s times 1 minus r is this. And if r is not 1, this is not 0. So I can divide by it, and there's the formula that we derived. So that's a direct proof of the geometric series formula for a finite geometric series. Let's do another example, this one dealing with internet addresses. Okay, so in order to communicate effectively, each computer in a network needs a distinguishing name called an address. For the internet, this address is currently a 32-bit number called IP, Internet Protocol Address, although 128-bit addresses are being phased in to accommodate the growth of the internet. For technical reasons, some computers have more than one address, whereas other computers, which use the internet only sporadically, share a pool of addresses that are assigned on a temporary basis. Like phone numbers, IP addresses are divided into parts. One, the network ID, specifies the local network to which a computer belongs, and the other, the host ID, specifies the particular computer. An example of an IP address is this, and it is in binary, where the 32 bits have been arranged in groups of 8, and we got 4 groups of 8. 1, 2, 3, 4 groups of 8. 4 groups of 8 for easier reading. And to make the reading even easier, IP addresses are normally written as dotted decimals. So they'll change this to a decimal, and they'll dot this to a decimal, this to a decimal, and this to a decimal. That means base 10. And when you do that, each of those decimals will be a decimal number between 0 and 255. For instance, the address that we have up here translates into 140.192.32.136. Now, in order to accommodate the various sizes of the local networks connected through the internet, the network IDs are divided into several classes, the most important of which are called A, B, and C. Those are starting the largest with A, and those other two get smaller. In every case, a host ID may not consist of either all zeros or all ones. Class A networks IDs are used for very large local networks. The leftmost bit is set to 0. That makes it a Class A, and there's the rest, and the is set to 0, and the leftmost 8 bits give the full network ID. The remaining 24 bits are used for individual host IDs. So you see you have a lot of IDs for host IDs. However, neither 000 or this can be used as a network ID for Class A IPs. Class B IDs are used for medium to large local networks. The left 2 bits are set to this. That tells you, that you're using a Class B network. Then you have that network ID and that host ID. Now you have fewer host IDs in this case. A Class C network are used for smaller networks. You have a big old network ID, 110 are fixed. The rest of them can be duped, and the remaining 8 bits are used for individual host IDs. So here's some problems. Check that the dotted decimal form of the address that we had is in fact this. Okay, sorry about that, perhaps discontinuity. So what we're going to do is we're going to change all of those numbers into decimal. And so here we change this into 140, this into 192, this to 32, and this to 136. How many Class B networks can there be? Well, we have to say how many numbers can we, we put the numbers in here, and what does that give us? Okay, well, in each one of those we can put a 0 or a 1, and so and there's 14 positions there, so it's 2 to the 14th, or 16,384. Part C. What is the dotted decimal form of the IP address for a computer in a Class B network? Well, in a Class B network, this is what you can have for the host ID. So you have to think about the network ID gives you this from here to here. So it's dotted decimals. That ranges from 128.0 to 192.255. Thus, these are the ranges that you can have. And so you have to think about how many numbers are here, but you can go from W, so it's going to be the form W, X, Y, Z, where W can go from here to here, X can go from here to here, Y goes from 0 to here, and Z goes from 0 to 255. However, X and Y are not both allowed to be 0 or to be 255. So those are the ranges that you can have. Those are the decimal forms. Now, the last problem here asks how many host IDs can there be for a Class B network? So you're saying how many host IDs can you have here? Well, for a Class B network, 16 bits are used, having two choices, either 0 or 1 for each one. So this is going to be 2 to the 16th or 65,536 host IDs. But because 2 of these are not allowed, all zeros and all ones, we have to subtract 2 from that number, and we get 65,534. A lot of counting involved in internet addressing. Let's move on to something perhaps tamer than that, or at least not as computational. This is called, but it is important, it's called the inclusion-exclusion rule. And basically what it's saying is, if you have A and B and the overlap, if you take the number of things that are in A and the number of things that are in B and add them together, they're not disjoint in this picture, and that means you have to subtract off where they overlap because that was double counted. And in general, what that's going to say is, well, here's the statement of it. So the number in A union B is the number in A plus the number in B minus the number in A intersect B. That's really even true when they're disjoint, because if there's disjoint, this is a 0. But we can go to 3 sets, and if we had 3 sets that potentially overlap, this is the number in A union B union C, and we take the number in A, the number in B, and the number in C, we have to subtract off the pairwise intersection. So we subtract this off because this was double counted. We subtract this off because it was double counted. We subtract this off because it was double counted. But when we subtract off things that were double counted 3 times, we have to add back in what was common to them. You might want to draw a Venn diagram of this to make it more clear to you. Let's use this in a couple of examples. Here we're counting the elements of a general union. So we say how many integers from 1 to 1,000 are multiples of 3 or multiples of 5? Well, let's talk about that. So if we look at the multiples of 3, what we're going to see is that there are going to be, I guess I start here. So every integer, we get 3 times 1, and we get 3 times 2, 3 times 3, 3, 2, and 3 times 3, 3, 3. So you see what that tells us that we had 333 of those. Now if we look at the multiples of 5, we get 5 times 1, 5 times 2, all the way up to here. So I have 333 of these, I have 200 of these. But then I have to say, subtract off the intersection, because there are some numbers, like 15, that's a multiple of 3 and a multiple of 5. So this is going to be 1, 2, 3, all the way up to 66. So you see I'm going to add this number and subtract 66. So when I do that, I add this number and subtract 66, I get 467. That tells me how many integers from 1 through 1,000 are multiples of 3 or multiples of 5. This is the inclusion-exclusion principle. Let's look at problem B, and I think I made a bit of a typo here. How many integers from 1 through 1,000 are neither multiples of 3 nor multiples of 5? Okay, now that actually is the complement of what we're saying. There were 467 were multiples of 3 and multiples of 5. So by the set difference rule, there are 533 that are neither multiples of 3 nor multiples of 5. So we're actually using De Morgan's law to think about that a little bit. Let's do another example, and this is called sometimes a survey problem, and I like problems like this. It wouldn't surprise me if on midterm and final exams there might be something like this. Counting the number of elements in an intersection. So here's the story. A professor in a discrete math class passes out a form asking students to check all the mathematics and computer science courses they have taken recently. This must have been before COVID. She found out that out of a total of 50 students, 30 took pre-calculus, 18 took calculus, 26 took Python, 9 took both pre-calculus and calculus, 16 took both pre-calculus and Python, 8 took calculus and Python, and 47 took at least one of these 3 courses. Now we should note that when we write 30 students took pre-calculus, that means the total number of students who took pre-calculus is 30. We allow for the possibility that some of those students have taken one or both of the other courses. If we want to say that 30 students took pre-calculus only and did not take the other courses, we would say so explicitly. So we have some questions we have to ask, and we're using this data. This again is called a survey problem. How many students did not take any of the 3 courses? Well, 47 took at least one of them, so we're going to put a 3 out here because this inside has to add up to 47. So that was not hard. How many students took all 3 courses? Now that's going to be more involved, and let's start on that. This was easy. Okay, so we're going to say we have this, and by the inclusion-exclusion rule, and here we're saying how many students took all 3 courses. We're trying to find out what is the probability of the intersection of those 3 sets. But we know by the inclusion-exclusion rule that the probability of P union C union Y is the sum of the probabilities of the individual sets, and we subtract off the pairwise intersection, and we add back in the intersection of all 3. This is what we're trying to find. We have numbers for everything else, so we put all the numbers in, and we solve for this, and we find it's 6. Hence, there are 6 students that took all 3 courses. In general, you know if 7 of the 8 terms in the principal for 3 sets, you can solve for the 8th term. Okay, so to answer the question in part C, we better look at what that is. How many students took pre-calculus and calculus but not Python? Okay, well, how many students took pre-calculus and calculus? So pre-calculus and calculus are going to be 3 and the 6. Okay. How many students took pre-calculus but neither calculus nor Python? Pre-calculus was, well, wait a minute, what was, that was pre-calculus, Python is Y, good. Okay, so how many students took pre-calculus and calculus but not Python? Oh, excuse me. That is pre-calculus and calculus, but not Python, is going to be 3. That's just 3. I'm sorry. I was forgetting what Python was. How many students took pre-calculus, but neither calculus nor Python? So pre-calculus, but neither calculus nor Python, that would be 11. Now, the way you got this was you started with what was in the middle, and you added things back. And so that is how you figure out what these are to fill in. You really probably want to work through this example so you understand it. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all.